Hello, everyone. Thank you for coming. Am I on? Yep, okay. All right, so thank you for joining me today. I want to talk about putting together a data warehouse from Apache projects. All right, and let me give a little introduction of kind of where I'm going with this and why I say it that way. So there's a lot of questions now about how do I build, or there's a lot of talk now rather, about how do I build a data warehouse in Hadoop. And from the benchmarks you see posted out there, and I just want to be upfront and say I'm as guilty about this as everyone else, because I've done this too, that really, the benchmarks would seem to imply it comes down to only two questions. How much of TPCDS, or how many of the TPCDS queries can you run and how fast can you run them? That's sort of what all the benchmarks talk about. I'm not saying that's not important. It's important. But that's hardly everything, right? It's a little bit like just the engine, right? You need a good engine, your car needs a good engine, but you don't just want an engine, you want the entire car, right? You want everything. So what's in that everything that you want beyond just the engine? Obviously, the engine is there, and it's not really, a lot of the benchmarks tend to use TPCDS as the way to talk about it because it's a convenient thing that everybody can look at and understand. Well, what people really want is a full enough implementation of SQL 2011, or now SQL 2016 even, to do all their work. That's what they're actually interested in, right? But you're interested too in, can it store all my data, and where does it store it? What are my options there? Can I fit my whole family in, all my users, everybody who wants to do BI and cubes and data science and whatever else your users want to do with your system? Is there a place for them in this? Is it secure? Is my data going to get stolen? Can I govern it, right? Can I make it, can I keep track of what's in there? Can I know where it came from? Can I make sure it's used properly? Can I get data into it? Sorry, I couldn't, the gas caps on the other side of the car, I couldn't point to that in the picture. Can I monitor and manage this thing? Can I drive it? Can I make it go? Can I manage the life cycle of the data? Can I replicate and handle disaster recovery? Can I do workload management? This is what most users really mean when they say they want to do data warehousing, right? It involves all these things. Now, I'm not trying to say this is all it involves, but this is a good sample. Now, in the proprietary world, you would buy one product or one suite of products from some company, and it would claim to do all these things. Whether it did all those things or not, I don't know, but that would make their claim. In the open source world, we tend to assemble these from different packages, right? And so this doesn't tend to come, like Hive obviously doesn't do all these things. But there are open source projects that work on these things. Also being open source, there isn't one way to do this, right? For most of those dimensions up there I put up, there are multiple ways to put this together, or multiple options to satisfy that, which means that there's tens or even hundreds of ways to combine all those things and get a data warehouse. I'm not going to talk about all that because we don't have all day, and because I'm not an expert in a number of those projects. I'm going to talk about one way to put all that together, which just happens to be the way my company puts it together. No bias in the selection there at all. Anyway, so I want to talk about a collection of Apache projects that you can put together to make this happen. Now, I will show some things that are not Apache, one or two things that aren't even open source, because I feel like they're pretty important to the ecosystem, and I want to touch on how those play as well, right? So that's where I want to go with today's talk. But since everybody talks about the SQL engine first, everybody looks at the benchmarks, let's start there. What's an option in Apache for a high performance database that implements enough of SQL 2011 to get done what you need to get done? And our answer to that is Apache Hive. right? So let's do a little overview of Hive and kind of some things it's doing in this space that are interesting. Hive does have extensive SQL 2011 support. I've got a slide a little later where I'll cover kind of what's there and what's being added currently. It does support atomic, well, full ACID, insert, update, and delete. With new work, merge is coming as well to enable you to handle changes in your data. With the LLAP work, that can do a lot of in-memory caching and fast query response. And for a long time, it's had a number of security options, connected to JDBC and ODBC, which means it's compatible with every major BI tool, and it's proven at a large scale. So let's look at that scale question for just a moment. These are numbers, well, I think the top right is from our testing in the lab, so 100 million rows per second per node with LLAP. But these others are nodes from actual Hive, statistics from actual Hive users. These are not test conditions. So there are people getting 100,000 queries an hour out of their Hive cluster. Hive clusters that store 300 plus petabytes of data and clusters up to 4,500 nodes in size. So this is real technology out there doing real work at very heavy workloads. So I said it does a lot of SQL 2011. What all do I mean by that? Or what all does that cover? There's a lot up there, and I'm not going to go over it all. But I want to point out a few things. The stuff in the kind of tannish, beigeish color there is stuff that's new in Hive 2 and Hive 2.1, both of which have already been released by the community. So these include things like primary keys and foreign keys. Though the safety tip there is we don't actually check them. We trust you when you tell us that there aren't duplicates and stuff, but this is still very useful for optimizer planning, for understanding how to do joins between tables and such. Also the addition of yet more OLAP functionality, partition and order bys in user-defined aggregates. On the far right, the yellow that I have marked there as Hive 2.next, that's work that's actually already gone into Hive. It's in Hive's trunk. The Hive community has not produced a release that contains that yet. And I labeled it 2.next because I'm not 100% sure. I think that's going to come out in Hive 2.2, but the community hasn't quite sorted all that out how it's going to do the release train there. So, or at least I think they have now, but they hadn't when I made the slides. So I didn't want to put a number next to it, but some of the important things here are adding merge to ACID. So this is very important when you're bringing data into the system from, say, your transactional systems and you want to load it into a staging table and every 5 minutes merge it efficiently. In the past, with just update, each update statement required a scan of the table you were updating or the partition that you were updating in the table, which obviously isn't efficient when you have hundreds or thousands of updates in there. With merge, you can do that in a single pass, and you can let the system intelligently decide, am I going to do this as an insert or an update, depending on whether the road's already there, right? You might have heard of this as upsert in other systems. It's the same thing. Hive can now handle queries with multiple subqueries in it. In the past, it only allowed you one subquery at a time in the where clause. It can handle non-equijoins and intersect and accept also as well. So these are all important things that users kept telling us they needed this additional functionality to get their jobs done. And then finally in the light blue there, you see some things that the community is talking about, thinking about adding, but we haven't gotten to yet, which is continuing to fill out features that people need to do their data warehousing. So if you've attended any Hive talks in the last year or two, I'm sure you've heard of LLAP, which is the work to basically make Hive work well for very fast queries. Hive has worked well for a long time for the big heavy lifting queries, ETL jobs that needed to run for a long period of time. We wanted to preserve that. We wanted to keep that, so we didn't want to move Hive to a completely MPP type system, which tends to do better with analytics, but has a hard time sometimes with the bigger queries, which the traditional Hadoop paradigm handles much better. But LLAP handles those short queries very well, and it does that by caching the data across a number of nodes, sharing that cache across users in a secure way, and then pushing the query execution actually into those caches so that in many cases, when you're querying hot data, your query won't even hit disk at all. It will simply access the data that's already been cached. And these caches are aware at both the column level and the block level so that they will cache only the pieces that are hot. It's not going to have to cache an entire table or an entire partition. If there's 5 columns in that, say, table that everybody wants to read, those are the 5 that'll end up in the cache and the rest won't. So it's very efficient in that way. And it works over HDFS or any of the objects, other HCFS compliant file systems such as Isilon or against object stores like S3. So how does the performance work out then? So I have several charts on performance just to show, kind of give you an idea of where we're at. This is Hive 1 versus Hive 2. Hive 1 is using TES, not MapReduce, so still using newer engines, but versus LLAP. And the green there is Hive 1, the blue that is pretty small is Hive 2, and then the descending diagonal there shows you the percent speed up. So you see that we've made some very nice speed ups ranging anywhere from about, 225 times as fast to around 5 times. In fairness, this graph's a little selective. There are some that come out about the same. We cut that, we kind of cut off the right end there. But you get the idea that we've made quite a bit of progress there. So people always ask me, how does this compare to this or that, to this other thing? So we ran these numbers against Impala. Here's what we saw. LLAP did better on some, so LLAP is are we the blue or the green? I don't have a monitor here, so I can't. Green is Hive. Okay, so we're green and blue is Impala. So you see that there are some queries that we're faster on, some that Impala's faster on, and a lot in the middle that are about the same. Now, obviously, the Hive community is going to be happier when we're faster on everything. We're not there yet. We believe we will be someday. But still, this is, for us, very good validation of our approach that we're able to compete with a fully MPP store while still keeping our big data roots and our ability to handle the very large types of queries. Lately, a lot of people also ask us how we look against Presto. So this is a run we did internally against Presto, where we are again green and Presto's yellow now. Now, a lot of that, you see it's slower on those. It's because Presto doesn't do some optimizations that Hive does. If you manually rewrite your queries, you can improve this. But for example, in this case here, we saw that even after the rewrite, we were still faster, though not, only 1 order of magnitude faster instead of 2 because doing the rewrites. So I'm not trying to say that LLAP is faster than everything else in every case. What I'm trying to show is we've got the performance now to do a lot of the data warehousing type of work. One final chart here that you can chew on for a bit. This one's particularly fun. It's one thing to say, okay, here's the performance of my cluster when I've only got one user, that he gets the entire cluster, all 10 terabytes of memory or whatever is his. What can I do? So we looked at what happens when you actually run multiple users at the same time. So we did it at 5, 25, and 100 concurrent queries. And you can see the spread there of how the performance came out. What makes us really happy about this is even as you're scaling users, we're actually a little bit sub 1 on the slope there of that linear scale. So we're doing a little bit better than just a linear scaling there, which is actually very encouraging. Okay, enough about the SQL and performance side. Let's talk a little bit about storing stuff. You want this to be able to store a lot of data, obviously, this is big data, and more importantly now, I think, you want to be able to determine where that data is. It may not be all in one place, it may not be all in the same type of store. So obviously there's HDFS, that's been there forever, and obviously work well with that, but more and more we see people storing it in clouds, in S3, in Microsoft's Azure, Google's cloud, what have you. So how do we work with that, right? Hive does work in the cloud. It has worked in the cloud for years. But there are a few things that are not optimized yet for the cloud. And I want to just point those out and say that these are areas of active work. So object stores in clouds tend to not implement all of what Hive or other projects around Hadoop expect in a file system. So Hadoop was built originally on HDFS. In HDFS, certain operations like move are free or nearly free and atomic. That's not true in S3. There's actually no move. Move is really a copy from one bucket to another, which is neither atomic nor cheap, right? So that forces some changes in the way we handle data. In particular, when we ingest data, the traditional path in Hive, Hadoop, many other things in the ecosystem is write it all into a temp directory, and then at the very end do an atomic move to slip it into where you finally want it. That way your users never see half the data, and you can load it however long it takes you, that's all fine. If you have failures, you can weed those out before you do the move, all those sorts of things. In the cloud, that doesn't work, right? We have to redesign how we ingest data so that we can ingest it directly into the proper spot while still making sure that users can't see half-formed data, or half-stored data rather, and that they can't, and that they're not exposed to errors. If there's one task that writes half its data and then dies and you have to rerun the task, you don't want the users to see that half-baked data. You want that cleaned up. So we have to rework how that's happening. I put up the JIRAs there for both Hadoop and Hive and work that's going on to do that. Also, there's work to do to make ACID work better in the cloud, because it also assumed that moves were free or nearly free. And finally, I want to go back to LLAP here a little bit. This is someplace where caching shines really well, right? The difference between reading from HDFS and reading from memory is significant. It's very significant, as you saw in some of those earlier performance numbers. But it's even more significant when you're talking about going back to an object store. So it becomes important to cache well and intelligently, and it becomes important to be able to recover when you decide to throw something out of the cache, and maybe it's something you're not going to use all the time. It's not hot data, but it's pretty warm, and you're going to want it again in a few minutes. And so there's work going on in the LLAP world to enable flushing that down to SSDs on the local machine, where in case that data comes, if somebody asks for that data again, you need to bring it back, you only have to go to your local SSD, not clear back to the object store to get that data, kind of a backup cache, if you will. All right, now let's talk about everybody's not favorite topic, security. Actually, if you run this stuff, this is your favorite topic. If you build this stuff, you're like, this is just something we have to do, right? But this is important. You don't want people to steal your hard-earned data. So how do we secure this? And it turns out there's actually a number of projects in Apache. There's lots of projects in Apache that work on security. We combine 3 of these together to get this, to secure our system: Apache Knox, Atlas, and Ranger. And let me sort out a little bit how those play together and why you need, because you might be looking at this thinking, why in the world do I need 3 projects? Why can't there be one? And the answer is they all touch different dimensions of things. So kind of the first question of security is authentication. Who are you? You tell me who you are, but do I believe you? That's where Apache Knox comes in, along with Kerberos. Then there's authorization. Okay, now I know who you are, but what are you authorized to do? Can you read this data? Can you write this data? Can you remove it? That's What Apache Ranger handles that. Then there is audit. What did you do? Keeping track of it. This is useful for a number of things, not least of which is figuring out, okay, when there was a breach, when something went wrong, what trail did the perpetrator take? Or even just when something goes wrong, what set of steps were done that made it go wrong? And finally, you want to protect your data either at rest or in motion, right? If it's on disk, you may need to encrypt it. You may need to keep it encrypted as it's moving across the wire. This is something Apache Hadoop can do, but you need key management for that, and Ranger offers a key management store for that. I'll talk a little bit more about each of these. I'm not going to go in depth with them because there just isn't time to cover it all. I want to point out so I talked about Knox and authentication. What does Knox really offer here? It is a single point of sign-on and a single point of integration with your security system. So you have LDAP or Active Directory or both, plus 3 other things that you need to integrate with. You don't want to have to connect Hive to that, Hadoop to that, all your pieces. Knox gives you one place to connect that. It also gives you one machine with ports you can open to communicate to your system so that you don't have to open ports to every machine in your cluster, which will make your security people much happier. Now, of course, Hive itself already offers basic SQL authorization, grant, revoke, who has the rights to read this table, who has a right to create tables. That's in there out of the box, you can use that. If you want more sophisticated security, that's where Apache Ranger comes in. So it can do those things, of course. It can do column level security as far as blocking certain users from seeing certain columns. But it can do a couple of other things that I think are even more interesting. It can do row level security. So in this example, we have users in different regions of the company, one on the eastern region, one on the western, and there's a company policy that people in the east can only see eastern data, people in the west can only see western data. How do you approach that? Now you could create separate tables and give permissions on them, but that means if you want to query all the data, you have to do some funky union. And with 2 tables, maybe that's okay, but when you have 10 regions, that's just untenable, right? You can create views, so you have one base table, you create a view that's the east, a view that's the west, but again, that becomes a maintenance headache, and especially as you grow regions. What Ranger gives you the ability to do is define policies that say users in this region can only see this data, and that's expressed as a where clause that you see up here. So the user actually writes this query, select star from customers where total spend is greater than 10,000, but working together with Ranger, Hive actually rewrites that query to have the where clause in there that limits what the user can see. And the same thing happens over here on the eastern side. So these users aren't even necessarily aware that they're seeing a portion of the table. To them, they're seeing the table, but they're seeing the part that you've allowed them to see. Similar is there may be columns that you need to mask, or you may want users to be able to see that they're there, but you may want them to see their only partial values or no values at all, depending on their authorization level. So let's take an example. Let's say you have a table that includes the tax identification numbers, what in America we call social security numbers of users. And you may want to show the last few digits. I don't know about here, but at least in the US, it's common if you call your bank, the way to identify yourself is give the last 4 digits of your tax ID. The bank clerk doesn't get to see all of your number. You don't want to show him or her that, because then you're compromising the security of the customer. But the last 4 is enough that the customer can give those, the bank clerk can validate that, and then that way they know I'm me when I call on the phone, or at least the odds are decent that I'm me. You may want that feature here, right, where you have users that you want to be able to select a column, and you need to be able to see part of the data in the column, but not all of it. Again, Ranger can do that. It can apply a masking function. It can apply one-way hashes, these sorts of things that enable you to still show the data, potentially for things like one-way hashes, still join the data without actually revealing the underlying data that shouldn't be shown. So That is actually done in conjunction with Apache Atlas, which is the one that tags what data should and shouldn't be shown. So if you have personally identifiable information, which we often call PII, that's where Atlas can tag that, and then you can say, here's a policy of who can see that, here's a policy of who should be masked, here's a policy of who shouldn't see it at all. In addition to those kinds of policies, you can do things like geography-based policies. You know, if you can't see data from Germany unless you're in Germany because maybe it's illegal to export it out. Time-based policies where data is only accessible at certain times of the day so that your users aren't going home and querying the database at home and doing who knows what with the data, as well as prohibitions against certain operations. For example, in the US healthcare rules, you cannot resolve data. If you have a rural region where there's not a lot of people, you're not allowed to resolve the data down to a certain point below which it would be fairly obvious, even without the person's name and address, who you're probably talking about, right? If there's only a few hundred people in a particular small town and you're able to narrow down the results of a query, you may be able to guess who that person is without knowing their personally identifiable information. So you have to put in policies that say things like, if this query would return less than 200 rows, you can't run the query. That you can do that kind of stuff as well. All right, I'm gonna have to speed up because I'm running out of time. So governance, again, this is Apache Atlas. So what does governance mean? It means a lot of things, but I'm gonna highlight two things that this provides, one of which is lineage. How did the data get here? And this isn't just how did it move around inside my warehouse, it's where did it come from before it got to my warehouse? Did it go through, you know, did I load this off of a transactional system? Did I stream it in via Kafka? Those sorts of things, right? So keeping track of how data comes into your system and how it moves around inside your system. And then also building a catalog of what data you have. One of the challenges with a data lake is how do you know what's in there? Especially as you onboard new users, how do they find the data they want? How do you keep them from recreating data that's already there because they didn't know that it was already there? That's where creating a data catalog comes in. It helps users find things. It also helps you standardize what is the meaning of user in your system. And, or sorry, not in your system, but for your customers. If you have users out in the world that use your application or use your product, I guess customers, what's that? How do you define them? How do you how do you segment them? All those things can be defined here so that everybody in your company is using those same set of definitions instead of the marketing department defining customers one way and the sales department defining them another, which won't end up the way you want it to end up. All right. So how do I, can I support my users on this? Can I do BI? Can I do cubes? Can I do data science? There are a number of projects in this space covering different areas. Druid, AtScale, Apache Zeppelin, Apache Spark. I'm going to touch just briefly on a few of these. So what is Druid? Druid is a technology developed at MetaMarkets and a few other companies that focuses on building what amount to, from a data warehousing perspective, OLAP indexes that enable very fast drill down and queries, the kinds of queries that you tend to want to do in data cubing. And so there's work going on in Hive currently to integrate Druid with Hive so that you can still use SQL, you can still get all the security of Hive, the JDBC and ODBC connectability, all that stuff, and have it access Druid underneath. Now in the initial implementations, you have to actually know to go hit that other table. Our eventual goal is to remove that need and that the optimizer would just be able to figure out, okay, I can answer this query actually faster using this index over here that happens to be in Druid, and I'll do it that way, right? So that we want to get to where we're able to answer those cubing type queries very well and quickly. Another technology in the same space is AtScale. This is a proprietary technology that will define these cubes keep some of them internally. In cases where the question can't be answered from the cube, it will go to Hive via LLAP and still be able to answer the query. Obviously not quite as quickly as if you've got an in-memory cube, but still very efficiently. And then I want to talk just a touch about Spark. Obviously, Spark's a huge thing. It can do lots and lots of stuff. Most people using Hadoop today are also using Spark. You want to enable your data scientists, your data engineers to use Spark, but you don't want to give up all that security and governance and other things I've been talking about, right? Spark, by its nature, doesn't offer as many points to secure it because it is a very versatile tool. It can talk to data, can read files directly off HDFS or whatever your storage is. That's very useful, but it also puts limits on how well you can secure it. You can't do column level security, column masking, all PII, all those sorts of things if you're giving the users direct access to the files. So how do you handle that? How do you take this secured data and still get it to your Spark users? And so we've integrated Spark with LLAP so that you can get that data quickly and still securely. So how this works is in the Spark client, you actually say you want to connect to Hive. It sends the query it's going to run to Hive Server 2, which does the authorization on it and make sure that you have the permissions to do that. It then gives back Spark a signed bundle of goo that Spark hands to LLAP, and LLAP can then stream the bits to Spark. And that way, we can still handle all that security and governance and still let users read it through Spark. All right, we've been talking a lot about what you can do. We haven't talked so much about how people do it. People need tools to work on all this. Lots of people have their favorite tools. One of them that we offer is Apache Zeppelin. This can connect to Spark, to Hive, to anything really that has a JDBC driver, a number of other systems. This is a quick and easy way for your data scientists and your users to write queries. You can write bits of Scala or Java in here if you're doing Spark. You can write Hive queries, and you can quickly visualize out what you see. Right? So you get lots of tooling here that applies across your system. Now, I haven't had a chance to touch on everything that I put on that chart because, well, I said I wasn't going to. I'm not going to talk in depth about all these things because I'm running out of time. But there's more here, right? There's other projects involved, and I've only touched on some of them. But I wanted to put up kind of the vision of what does this look like, of this is what we want to see for Apache-based warehousing in, based on Hadoop, where you take all these, you put them together and you have a fully functional data warehouse. Now, I have skimmed across a lot of things. There are talks on most of these things more in depth later today and tomorrow, which I've put up here. I strongly encourage you, if you're interested, what I talked about, excited, want to know more details, come to these talks, hear from the people who are building this stuff, and ask them lots of questions. Okay, with that, I think I'm to my question part. So anybody have questions they want to ask me? Yes?
In one of the slides, you have shown this unified SQL and MDX layer.
Mm-hmm.
Where is this coming from?
Okay, so the question is, in this slide, actually, I put up SQL and MDX. Well, I think it was in an earlier slide, too, but MDX is also there. I just want to be clear, there's no MDX support in there now. At scale, I believe, does support MDX, but none of the Apache ones do yet. But that's where we want to drive to, is enabling Hive to also understand that so that people can do MDX queries if that's what they want to do. So it would come through Hive Server 2 the same as your SQL does. Yes?
What is the limit of data that you can put within the cache?
What is the limit of data you can put within the cache? How much memory will you give me? I mean, I don't know if what you're asking is how efficient, like how wide can we make the LLAP cluster and make it efficient still. I don't know that we've tested that yet. Gunther, what's the maximum cluster size we've tested at for LLAP? Yeah, what's that? Okay. Well, so it's the kind of maximum we've tested at so far is a few hundred nodes, and that seems to work well. But honestly, LLAP will use the memory you give it, right? It is, no matter how much you give it, it will use it all, if it can efficiently, if there's data to use. Okay. Other questions? Yes?
In some summits last year, we have heard about Arrow.
Mm-hmm. Okay, so the question is, how does Arrow fit in the picture? There is a talk on Arrow. It's later today or tomorrow, I'm not sure when. I would encourage you to go there and ask them that question again. Arrow, as far as, well, no, because in fairness, I'm not an expert in Arrow, so I'll give you my understanding of it and how it fits. Arrow is really focused on being an in-memory representation of data so that they can move between different systems, right? Hive today doesn't support Arrow as far as I know. I don't think the Arrow guys have added it yet. It could. It would be a nice way to transmit data between Hive and, say, some other system if it wanted to do that. But that's really its focus. How do I efficiently transfer this stuff in memory without having to do lots and lots of changes on the data because I'm moving from, say, I don't know, Hive to Presto or whatever. Yes?
Does LLAP do compression, or do you compress data with them?
So the question is, does LLAP do compression? Sort of. So LLAP works, well, originally only on ORC files. It can now also work on other types of data, but we'll go with ORC as the example. ORC can be doubly compressed. So there's what we call an encoding phase, where we take the strings and make dictionaries out of them, and then where integers and strings are, the dictionary encoded strings are then run length encoded. That is kept in memory. So when we store them in memory, we do that encoding. But there's a second level of compression using Snappy or LZO or whatever you want to use in your system, and that's not done in memory. So it's kind of a trade-off, right? Because the more you decompress, the faster you can access, obviously, but the more memory you take up. So we took that middle spot where it's still encoded. That means when you're accessing the data, you still need to do the conversion, the decoding and conversion into vector batches to pass into the operators, but you don't have to do the full LZO or Snappy or whatever decompression, which tends to be much lengthier or take a longer time. Yes?
I'm asking, can you use the security aspect that you presented now to mask a part of the database in order to enhance performance of the queries?
Okay, let me make sure I understand this. Can you use the performance, can you use security to enhance the performance?
Yeah, to enhance the performance of the queries. For example, if you mask, for example, one half of the data by geographic criteria.
Oh, would that speed it up? Basically, can the optimizer take advantage of the fact that you're not reading half the data? Depends on how you've partitioned your data, but in general, yes. Because the query is rewritten before it gets to the optimizer would already see it with that data excluded. And so if it's such that that allows it to drop partitions or read less files, it would figure that out. I'm being told my time is up, so I have to be done. Thank you very much for your time. And yes.